Welcome everyone. My name is Szymon Migacz. I'm working for NVIDIA as software engineer in CUDA math libraries team. It's the first time I'm presenting at GTC, and I will try to do my best. In the next 25 minutes, I will be talking about 8-bit inference in tensorrt. In other words, I will tell you how to make your networks run up to 4 times faster with reduced precision. And hopefully, by the end of this presentation, you will know more about our method, and you will be able to apply this to your own models. So let's begin. Technical issues. It works. OK, so I will be talking about the work which I did a few months ago. And the main goal here was to develop a fully automatic method which can convert FP32 convolutional neural networks into int8 without significant loss in accuracy. And here we assume that the network was trained in FP32 and that no actions related to int8 were taken during the training. So this method can be applied to any publicly available pre-trained models, like, for example, AlexNet, VGG, GoogleNet, ResNet, and others. So why are we doing that? It's mostly because int8 arithmetic is significantly cheaper and has higher throughput, requires lower memory bandwidth, and less storage. The main challenge here is that int8 has significantly lower precision and dynamic range than FP32. The key idea behind our method is that we want to minimize the loss of information when we are doing this conversion from FP32 to int8. It applies to both weights and activations. Presented method was implemented and tested in tensorrt. It's going to be released with tensorrt 2.1, and this is going to happen soon. There is another very important thing. This method doesn't require any additional fine-tuning or retraining of the models. This means that users don't need to have access to very large training data sets or spend many hours while running backpropagation. Here's the outline of the presentation. First, I will talk about int8 compute. Then I will talk about quantization of weights and activations and about calibration of the network. Then I will say a few words about the typical workflow in tensorrt. At the end, I will show accuracy and performance results from our int8 inference with standard networks like AlexNet, VGG, ResNet, and others. And this slide explains the main challenge with int8 inference. With 8-bit integers, we only have 256 values to work with. And it's almost nothing compared with the range and precision of 32-bit floats. That's why we have to be really careful. There is not much space to make mistakes. We have to be right on point with our quantization. We did this work because NVIDIA Pascal architecture introduced a new hardware instruction. It's called DP4A, and basically it's just a 4-way dot product with accumulation in 32-bit integers. It's available since SM61. It processes 4 inputs at the same time, therefore it's much faster than FP32 arithmetic. From that, we are expecting up to 4x speed up. And with this instruction, we can very easily and efficiently implement int8 dot products and matrix products. As I was saying previously, our main goal here is performance and no accuracy loss. Therefore, our method has to be simple and compute efficient. We just cannot afford a lot of extra bookkeeping and auxiliary computation during the inference. And obviously, we cannot expect weights and activations to be in int8 range from -128 to +127. So we have to apply some sort of range scaling, and the simplest choice here is a linear quantization. In this representation, each tensor has just one FP32 scaling factor. It's the one number for the entire int8 array. And in general, we can also have FP32 bias. This is also one number for the entire tensor. The question right now is, do we really need bias? With bias, our math gets slightly complicated. Let's look at this example. Here we have 2 matrices A and B, and each matrix has its own scaling factor and bias. If we multiply those 2 matrices, then the 3 terms containing bias are produced over here. And those terms add additional compute and require additional registers, temporary storage, and so on. But what happens if we remove this bias and use only scaling factors? Then those three terms are gone and everything becomes much simpler. And in our experiments, we found that bias is not needed for good accuracy. So we are using only scaling factors because it's easier and faster. That way our gems are simpler. It's just a scaled regular gem without additional terms. And it can be very easily expressed in terms of standard plus API. So this is our final numerical representation. It's symmetric linear quantization where each tensor has one associated scale factor and there is no bias. Now the question becomes, how do we set this scaling factor? Since our quantization is linear, then the easiest option is to look for the maximum absolute value in each FP32 tensor and set the scaling factor so that it maps this maximum absolute value to int8 127. It's shown here in this picture. This is our input FP32 tensor. We look for the maximum absolute value and map this value to 127. Everything else is quantized linearly. Unfortunately, there is a problem with this simple method. If we do only that, then in general, there is a significant accuracy loss, especially in deeper networks like ResNets. Therefore, we have to do something different here. The second easiest option is to map only a subset of the entire range into int8 values. In other words, we will quantize with saturation. We pick a threshold, and numbers beyond that threshold are going to be saturated to plus or minus 127. And here's the picture. We have three numbers that are smaller than minus threshold, and those numbers are going to be saturated and represented by minus 127 here. And numbers within the threshold are going to be quantized linearly, as before. Okay, so our experiments shown that if we do this saturation for weights, then there is no change in accuracy. So for weights, we are using this first simple method where we just look for the maximum absolute value and map this to 127. But for activations, quantization with saturation significantly improves accuracy. So the next question is, which value of the threshold is optimal? Or in other words, how do we optimize this threshold selection process? As you might expect, it's always a trade-off between range and precision of our int8 representation. Since we just have a fixed number of 256 values to work with. And here I'm showing histograms for activations from different layers of different network. On the left, we have a convolutional layer from VGG. In the middle, there is one of the layers from ResNet 152. And on the right, we have a pooling layer from GoogleNet. Important thing here is that there is a logarithmic scale on the y-axis and linear scale on x-axis. As you can see, the distributions here are completely different. So our method has to be general and work well with all types of distributions. When you think about this for a while, then you will realize that neural networks are just a flow of information. You start with a data layer, then you propagate your signal through many different layers, and this information needs to reach the last layer in your network, which makes the final decision. It could be either classification or regression, it doesn't matter. Therefore, we want to minimize the information loss, because conversion from FP32 to int8 is just a re-encoding of the same information in a different numerical format. And this is the key idea behind our method. Int8 model has to encode exactly the same information as the original FP32 model, and we want to minimize the loss of information during this conversion. This loss can be measured by Kullback-Leibler divergence. It's also known as relative entropy or information divergence. And here is the formula. Let's say that we have two discrete probability distributions P and Q. Then KL divergence of P and Q is just a sum of P times the logarithm of P over Q. And the intuition here is that KL divergence measures the amount of information lost when one distribution is used to approximate the other distribution. And this is the high-level overview of our method. We call this process the calibration. So what do? We first run FP32 inference on the calibration dataset. I will explain this term in a minute. Then, independently for each layer, we collect histograms of activations from this FP32 inference, and then we generate many candidate quantized distributions with different saturation thresholds. And we pick the threshold which minimizes the KL divergence of quantized distribution with respect to the reference distribution from the FP32 run. And the important thing is that this entire process takes just a few minutes on a typical desktop workstation. This algorithm has a linear complexity with respect to the number of layers in your network, so this is not a brute force search, and it works very well even for very deep networks like ResNet 152. Now let's talk about this calibration dataset. First of all, it has to be representative and diverse. So for example, if you want to calibrate a network trained on ImageNet, then you have to include examples from as many classes as possible. You cannot only use pictures of cats and dogs and expect it to work well. Your calibration dataset has to be diverse. Ideally, this dataset should be a subset of your validation dataset. In our experiments, we have shown that for ImageNet type of networks, it's enough to use around 1,000 images for calibration. So it's only a fraction of the entire validation data set, and it's nothing compared with the entire training data set. So let's talk about the results from calibration. I will present histograms of activations from various networks and saturation thresholds produced by our method. Here's the first example. It's a histogram from one of the layers in GoogleNet. On y-axis, we have normalized number of counts, and scale on this axis is logarithmic. And on x-axis, we have activation values after a ReLU. Green points are just data points from our histogram, and the white line represents the saturation threshold produced by our method. So everything to the left of this white line is going to be quantized and represented by int8 values from 0 to 127. And everything to the right of this white line is going to be saturated to the threshold value and represented by int8 127. As you can see, this distribution is very regular. So the method decides to saturate only a few outliers in that region. Now, slightly more extreme example. It's a histogram from one of the layers in ResNet 152, and here we have a long tail of outliers. I will show you the distribution before and after saturation. It's the same distribution before and after, and as you can see, all those outliers over here are going to be saturated to this threshold, and after this saturation, our distribution looks like that. Therefore, in this small region over here, we'll have available all int8 values from 0 to 127 to increase the precision of our representation where it matters the most. Here is yet another extreme example. It's also from ResNet 152. And in general, ResNets tend to have this type of distribution. Here is a long tail of outliers. And all those values are going to be saturated to this white line. So we will have all int8 values available in this small region where the accuracy matters. This is yet another example. It's a pooling layer from AlexNet. As you can see, this distribution is very regular. It doesn't have any outliers. And our calibration method correctly decides to represent this entire range of activations without any saturation. Same story is here, but with a different shape of a distribution. It's a pooling layer from GoogleNet, and there is also no saturation here, as you might expect. Now I will talk about workflow in tensorrt. Here's a typical workflow. So first, you will need a model trained in the FP32 floats and a calibration dataset. Then tensorrt will automatically run inference in FP32 mode on this calibration dataset. It will collect statistics, and by that I mean the histograms of activations. It will run the calibration algorithm, which will determine the optimal scaling factors, and it will also quantize weights into int8. After that, you get your execution engine, and you can completely forget about the calibration and calibration data set. This int8 execution engine can be deployed to, for example, to servers in the cloud or to the self-driving cars and so on. You just get your engine and you can ship it. Now let's talk about the results. First about accuracy. Here's a table with results from standard networks like ResNet, AlexNet, GoogleNet, and VGG. And numbers are from tensorrt 2.1 with all performance optimizations enabled. And networks were run on ImageNet, ImageNet validation dataset. Each batch contains 25 images. Accuracy was measured on 500 batches, which were not used during calibration. And there are two important things to observe here. First thing is that the accuracy of int8 inference is very close to the FP32 baseline. The differences in top 1 and top 5 accuracy are always less than 0.5%. Usually it's even less than that, around 0.1 or 0.2%, so it's not a lot. And the second thing to notice here is that the results are more or less independent of the size of your calibration data set. Here I'm showing results from calibration on 5 batches, on 10 batches, and on 50 batches from the validation data set. And as you can see, the results are very stable. And I'd like to mention here that we have also tested our int8 approach with a few internal object detection networks for self-driving cars, and the accuracy was also very comparable to the accuracy of the reference FP32 models. Now let's talk about the performance. Plot on the left shows the relative speed up of int8 inference versus FP32 inference, and it was measured on Pascal Titan X. For batch size equal to 1, the speed up is not that great. It's mostly because Titan X is a really big GPU, and with a batch size equal to 1, there is probably not enough parallelism to fully saturate this huge GPU. And for larger batch sizes, the speed up of int8 inference and versus FP32 baseline is from 2.5 to 3.3x. On the right, we have numbers for Drive PX2. It's a much smaller GPU. It's intended for self-driving cars. It's much smaller, and therefore it's easier to saturate it. So we are seeing some very decent speedups even for batch size equal to 1. And for large batch sizes, the speedup is also around 3.3 to 3.5x. And there is one thing to note here. Images for ImageNet networks are relatively small. Typically, networks for, let's say, self-driving cars, they work on much bigger images. The images are a few times larger, so the network has more computations to do. Therefore, it's much easier to saturate a very big GPU, for example, like Titan X, and those networks will get much better speedups, even for batch size equal to 1. And here is a list of open challenges and improvements in the implementation in tensorrt. So first of all, we could use unsigned integers to represent activations after ReLU to improve the precision. Right now, we are just using signed integers everywhere. RNNs are still an open research problem. We are working right now. We are working on that right now, so I don't have any results to show. The third thing is an iterative fine-tuning of saturation thresholds. It's possible that it might improve our accuracy even further. The last one is an addition to tensorrt API. We could expose API for accepting custom user-provided scale factors so that people can experiment with their own calibration algorithms, and maybe they will be able to develop something even better. Okay, so let's proceed to the conclusion. We have introduced an automated parameterless method which can convert FP32 convolutional neural networks and run inference in int8. This method uses symmetric linear quantization. It's for both weights and activations. And the key idea behind our method is that we want to minimize the amount of information lost when converting from FP32 to int8. And we were able to show that popular publicly available convolutional neural networks can be converted to int8 and executed up to 4x faster without significant loss in the accuracy. Here are some additional resources. We will publish a white paper with the description of the method. It will contain additional details which were not included in this presentation. And as I was saying, tensorrt 2.1 is going to be available soon. It will include sample int 8, which you can use to test your own models. Also, there is another tensorrt talk at GTC this year, and Chris will be talking about deploying unique deep learning networks as microservices with tensorrt, user extensible layers, and GPU REST engine. It's on Tuesday at 4:30 p.m. Also, if you want to know more about tensorrt and other libraries, then there will be free Connect with Expert sessions. First one is today at 2 p.m. The second one is on Tuesday, also at 2 p.m. And the third one is on Wednesday at 3 p.m. And it's a great place to ask your questions and talk with the tensorrt developers. Okay, that's all I have. Thank you very much for your attention. I will.
Thank you very much, Szymon. We have time for a couple of questions. If anyone has one, there's 2 microphones that you can approach.
Hey, it's a pretty interesting talk. Can you tell me about the KL divergence function? Is it smooth? When you're searching around, you did hopping around to sample it?
No, we just generate saturation thresholds linearly. We generate like 2,000 different saturation thresholds and run 2,000 KL divergences and pick the one which is pick the threshold which minimizes the divergence.
Okay, but so that function's not smooth? That's why you hop around?
Well, perhaps we could use some algorithm to look for the minimum, but the problem here is that this process takes only a few minutes, so there is no reason to use some kind of heuristic or gradient descent method to look for this minimum. You do this only once for your network, so it's not that long. It's only a few minutes.
Okay. Do you have any other questions?
So this theory behind this, what you explained, he applied to the API actually. It doesn't have to be tensorrt
Could you repeat the question?
Okay, so the question is if this method can be applied to a different framework like TensorFlow and others. And the answer is that yes, this is just an algorithm. You can apply it everywhere in Caffe, Torch, TensorFlow. But we did it in tensorrt because in tensorrt you get many additional optimizations like horizontal fusion of the tensor, vertical fusions, concatenations are eliminated from your network. So there is a lot of performance benefits of using tensorrt.